Okay, so second to last lesson of the semester, we're on what's called domain and range. You will hear that over and over again, every unit moving forward and every math class moving forward. All right, so for the warm up, we have number of barks. Earlier, you saw a situation where the total number of times a dog has barked was a function of the time in seconds after its owner tied its leash to a post and left. Less than 3 minutes after he left, the owner returned, untied the leash, and walked away with the dog. First question, could each value be an input of the function? And if so, tell me which one. So table 1, could all of those values, 15, 84 and a half, 300, be inputs to that situation? Say no, and which ones could not be? 84 and a half. Now, for those of you that were kind of unsure what it was even asking, first you need to figure out what the input in the situation is. So say that we were graphing this. We have two things being compared. Number of barks and time in seconds since the owner left. What would go on the x-axis? Table 2, could you tell me what would go on the x-axis? Yeah. Input goes on the x-axis. So the two things being compared, would it be number of barks or time since the owner left? Okay, good. Time is usually on the x-axis. There's times where it's not, but it's whatever is independent, right? Like we can't change the time, and the barks kind of depend on how long it's been since the owner left. So time would go here. That's what my input is. And then my output would be the number of barks since the owner left. So then table 1, does that change your answer at all? Is it possible to have 84 and a half seconds? So 84 and a half could be an input. So let's, this one can be an input. So I'll start the next. Could 15 seconds be an input? Could 300 seconds be an input? Okay, the only reason I need to check that one is because it did say 3 minutes after the owner left, the owner returned. So they must have stopped at 3 minutes. All right, but our time is in seconds. How many seconds are in 3 minutes? 180, good, because 60 seconds each minute, right? 60 times 3 is 180. So actually, the 300 can't be, and for the reasoning why, it's because there are only 180 seconds in 3 minutes. So anything over that wouldn't be measured, right? They're only measuring from the time the owner left and the time the owner returned. Okay. But good. So you can have decimals of seconds. That is possible. That's why the other two are possible. Table 3, could each of those values be an output? And then if so, which ones could be an output? So let's remind ourselves, outputs are the what of a function? The y, good. So in this situation, what did we say had to go on the y-axis? On the y-axis? Okay, so could I have 15 barks? Could I have 84 and a half barks? No. Could I have 300 barks? Yeah. Possibly. If you heard a dog bark a lot, they could bark like a few barks in 1 second, right? So yeah, I would say that that 300 is still possible, but you can't bark half a bark. So for this one, the reasoning, you could say cannot have half a bark. All right, so any questions on any of the reasoning or how we figure it out? What's the input? What's the output? Okay, and that's really what you need to do. Whatever random situation they give you, it's going to be two things being compared. For me, it's always easier to think like, okay, if I was graphing this, what would go on my x-axis? That's my input. What would go on my y-axis? That's my output. And then if you're even confused about how you figure out if it goes there or not, remember that trick I told you. You can make a D with the y-axis. That would be your dependent variable. And you can make an I, it's technically both, but you can only do with the y-axis. And that would be your independent variable. All right, how much time the dog barks depends on how many times the dog barks, depends on how long it's been, right? So that's how you know. All right, now moving on. Here's the goal for today. We are doing a combo lesson. 10 and 11 are both about domain and range. So I want us to have more time to review for the test. That's why we're combining it. And the goal is to find all possible inputs and outputs for a function and analyze graphs to learn about their domain and range. So you got to know what is meant by domain and range, and I'm going to explain that in a second. And then when given a description of a function in a situation, you can determine a reasonable domain and range for the function. So I'm recording right now. I always record the lessons from last year are usually linked in case you ever want to get ahead. Puzzle piece, it's separate, but they're both very short. I think one of them is even only 3 questions. So it's there for you, more so for extra practice so that you're ready for the quizzes, so you're ready for the test. But also, I meant to include it in the slides, but I guess I'll just tell you. I do have both study guides now available right at the top of Schoology. Right, so right at the top of Schoology, I put it there so that you have no trouble finding it. This is what you need to prepare yourself for the next unit test, which you are taking Tuesday. Okay, so this one helps you with the 100-point portion. That's why it's worth 100 class points. And then the one underneath it, when you click on it, it's going to be your constructed response practice test. And I already even have a submission from some people, so that's really nice. They're really prepared. But it's linked here. You could always do it on your own paper and submit. I plan to check it when you do binder checks, but this is what your constructed response test will look like. Also, if you want the paper already, they're in the bin. So are your reviews for your finals already in the bin? Yeah. So questions on anything? All right, I do have tutoring today, and then only 2 more Wednesdays after that. There's Saturday Academy this Saturday. If you have enough, you can expect an invite, you know, because you got to do whatever you need to do to at least pass. Otherwise, you got to sail through a whole nother semester. All right, now moving on. So I told you the lesson is called domain and range, so you should probably know what that is. Feel free to jot it down somewhere. You might just be able to remember it. I'll try to give you an easy way to remember it. But the domain of a function is a set of all the possible input values. So it's another way to say inputs. What else do we call inputs? X's. So domain is all the X's of a function. If you even want to shorten that definition, all the X's inputs of a function. And then range is on a different page. I don't want to flip because I know some people are writing. So I'll just summarize it for you. The range of a function is the set of all its possible output values. What else do we call outputs? The y's. So all the possible y's of a function. So an easy way that my students have memorized it in the past is Dr. XY. So you remember domain is all the x's, range is all the y's. That's really it. You can have domain and range of tables, of coordinates, of graphs, of situations. So we're going to practice mostly the situations because that's what you'll see on the test. But you just got to know domain is all the x's, range is all the y's. All right. So then we're going to practice that. I believe a card for is next. Let me check. Yep. So I'm going to pass out a set of cards. And in your groups, you will decide for each situation. You have 3 situations on your paper. What would be possible inputs and what are impossible inputs. So like, you know, earlier when we talked about it, you can't have 84.5 of a bar. All right, so that would go under impossible for that situation. And that was actually an output to maybe what you need in time. All right, like if we were looking at a time frame from 0 to 3 minutes, you can't have 300 seconds because that doesn't fit within the time frame. All right, so that's what you're listing. You're gonna have to kind of like keep track. That's why you have a note sheet on there. All these situations are printed, but your options are going to be on these little cards that I passed out. Okay, so I'm going to be one moment to pass it out, and then I'll start you on the timer. So situation 1, the area of a square in square centimeters is a function of its side length s in centimeters. This equation defines the function. So table 4, can you give me one of the possible inputs? Okay. Class, you guys agree? 6 possible? Okay, I was gonna say I don't see 6 on my list, but what is my inputs representing, like in the 2 things being compared? S, which is for side length. So can you have a decimal of a side length? Yeah. So that's why it's a possible one. So side length, and then I think area is on the other side. The area depends on your side length. Table 5, can you give me another possible input? Everyone else have them like already ready in your mind. This should be like a lightning round. Table 5, another possible input for situation 1. 9, class agree? Yes, you could have a side length of 9. And we're talking about what, centimeters? Yeah, you could have a side length of 9 centimeters. Table 6. What did you say again? 15, correct. Table 7, what's another possible one? 72. Table 8, another possible one. 0.8. Table 1, another possible one. Table 2, another possible one. Table, and I'm kind of running out of room. Let me move this up. All right, table 3, another possible one. And if there's not any more, you can tell me that too. (25/4). All right, yes, because that when you divide it, you get a decimal, and we already said we could have a decimal of a side length. So yeah. Table 4. Are there any other possible ones? Okay, table 5, are there any other possible ones? 3/5. Table 4, are there any other possible ones? Yes, no. Okay. So the book actually lists one more, and I think it is debatable, but they do list 0. Okay. So that's what the book says. You could argue with it, but sure. They're including the 0. For me, if you justify it either way, I would probably agree with you. 0 is a bit debatable. Table, well, I guess if these are all our possible, then we know what our impossible are. -3 and -18 for that one. Why are these impossible? Because they are negative. You cannot measure something, well, at least length. You can't measure a length and get a negative number. All right, so that's why. So I will include some verbiage that you might see. So for my possible inputs, if I'm summarizing them, you could really say all non-negative real numbers. Okay, so non-negative means positive, right? Real numbers means that it can be a fraction of a number. It can be a decimal of a number. If I wanted to specify just whole numbers, I would have said all non-negative whole numbers or all non-negative integers. But real numbers lets it be decimals and fractions and things like that. So then for my impossible ones, these are obviously negative numbers. That's why they're excluded. Okay, questions on that? All right, for the next two, when we go over them, we're just going to project the answer. So have them down on your paper, but look at situation 2 and 3 with the card sort. Determine which are possible, which are impossible. I'll project them in, I'd say, 3 to 4 minutes. A tennis camp charges $40 per student for a full day camp. The camp runs only if at least 5 students sign up, and it limits the enrollment to 16 campers a day. The amount of revenue in dollars that the tennis camp collects is a function of the number of students that enroll, and they give you an equation. If I were to look at a graph of this, what would go on the x-axis? So see the two things being compared. What was that? Okay, so would the revenue go on the x-axis?
No.
The revenue goes on the y-axis, right? Because the revenue depends on how many campers signed up. So then on my x-axis, it would have to be perfect. And there's limits on that. So when you read the description, would they run it with like 0 campers? No, because that's part of my impossible ones. They said they need at least how many? They need at least 5. So that's why 4 is not included, even though 4 is the number of possible campers. Not for this camp. You need at least 5, right? And then what's the most you could have? 16. So really all numbers from 5 to 16, except for what type of numbers? Decimals. Can you have a decimal of a camper? So if you were describing this, you would say all whole numbers or integers is what this curriculum seems to use. From 5 to 16. I don't like using integers because that could include negative numbers too, like negative numbers that are not decimals. But when you're saying from 5 to 16, there's no negative numbers in that. So that's one way they summarize it. That's why the only numbers that worked for this one were 9 and 15. Make sense? Can't have negative people, like you can't count a negative amount of people, can't have decimals of people, and these are outside the limitation. All right, now for the next one, situation 3. Here's the answer. Okay, now let me read it to you in case you didn't get that far. The relationship between the temperature in Celsius and the temperature in Kelvin can be represented by function K. Here's an equation for it, where C is the temperature in Celsius and K of C is the temperature in Kelvin. Now this one is kind of hard. We're comparing temperature to temperature. But what, based on this notation, would be my input? The C, which is for Celsius. So that means the Celsius temperature would be on my X and the Kelvin temperature would be on my Y. Now, I don't know if you know about temperatures, really, but can you have decimals for the temperature? Yeah, you can. Like your body temperature is like what, 90 degrees, 7 point something? Like when you take your temperature on the thermometer, right? So you can have decimals of temperature. Can you have negative temperatures? Yes. Like in really cold places, the temperature outside could be negative. So that's why for the possible inputs, it was all of the ones you could pick from. And there were no impossible ones for that one. All right, questions on that. When we say that all values are possible, you might see that as all real numbers, which includes decimals, fractions, negatives, positives, all of them. All right, so good exercise. We're gonna kind of just briefly look at some other things. Because in this one, all we talked about was the domain and what the domain could be. Based on what the range could be, that could be your continuous versus discrete graphs. So just kind of read this. If you feel like jotting stuff down, you can, but it's still about what we just did. All right, so same activities, but now let's talk about the outputs briefly. So if you look at the function where we talked about the side length of a square, that was situation 2, I think. Or situation 1. It was situation 1. We describe the set of all possible input values as any number greater than or equal to 0. How would you describe the outputs? So like for the area, can my area be negative numbers? No. Could my area be decimals? Yeah. And it could also be whole numbers, right? And it started at 0 because of course, no negatives. So you could sketch like what the graph could probably look like. When the graph is a line like this versus a bunch of dots, we call that continuous. So kind of sketch the graph, if you will. When both variables being compared can be decimals, then you'll use a continuous line. Now for the other situation about the number of campers, we talked about for the inputs, you can't have a fraction of a person, can you? For the money, you could have fractions of dollars, but if they're charging a specific amount per person, then you could really only have like certain numbers for your range. So this would be really good for your test stuff coming up, you're saying? But looking at these two graphs, do you think it would be better represented as a continuous line or a bunch of dots? We'll talk about that in your groups. We've talked about campers. You can't have fractions of campers. Get changed? No. Yeah, it should be the one with the dots. So if you kind of want to sketch that for situation 2, their graph would look something like that, because they're only taking 5 to 16 campers. According to this graph, they could take like 1.5 campers if they look at this point on the line. Right? So if they're only taking whole numbers, things like that, I should probably use dots for that reason alone. And then also the reason why we didn't connect these dots is because if they're charging 40 per person and we're starting at 5, 40 times 5 is 200. Could their revenue be like 210? Play into that. Play into that. All right, listen, does that make sense? Would their revenue ever be like $250? Okay, so if it's 5 campers, they're making 200. So they're charging 40 per camper. What about if it's 6 campers? How much does it cost? So really, actually, they couldn't make 250. So they're not charging like one person $10 or something like that. They're charging each of them $40. So when you're figuring out the range, you could have to do a little bit of math. So like 40 times 7 is 280. 40 times 8 is 320, right? It should be like in increments of 40. Does that make sense? So that's why the dots versus the line. Questions on that? All right, we're going to move on to the last activity that's on the back, which has, and I'll read you the situation. But you have basically 4 different graphs. And first, you're going to match them to the function. So here's the situation that's going on. A child gets on a swing in a playground, swings for 30 seconds, and then gets off. Here are descriptions of 4 functions in the situation and 4 graphs representing them. The independent variable in each function is time in seconds. Match each function with a graph that could represent it. So here's each function. First, you got to tell me, okay, based on this graph, is it function H, R, D, or S? And you have the descriptions and the pictures on your paper. What we'll do after that is decide domain and range. So once you think you've matched them appropriately, that's what we'll be doing next. You can jump ahead to domain and range. Difference for each function would be like what your y-axis would be labeled as. So for the first one, function H, the height of the swing in feet as a function of time since the child gets on the swing. I'll take a volunteer who thinks they've identified that one. Parker? All right. So we think function H goes with that one. All right. I agree. So the height of the swing changes, right, depending on how long you swing. It goes high and then it goes back down. It goes high and then it goes back down. So that one best matches it. I would agree. So that one could be height of the swing in feet as a function of time since the child gets on. So next one, function R, the amount of time left on the swing as a function of time since the child gets on the swing. Who thinks they've identified that one? Someone different. Serenity? Okay, the first one, matching to function R. All right, so the amount of time left on the swing as a function of time since the child gets on the swing. So say they're on the swing for 30 seconds. At 15 seconds, how much time do they have left on the swing? 15. At 20 seconds, how much time do they have left on the swing? So as the time continues, the time left decreases at a constant rate. So I would agree with that one. Good. Function D, the distance in feet of the swing from the top beam as a function of time since the child gets on the swing. Nathaniel? This one. And that one says that there's basically no difference throughout. So class, oh, that's function B. Like that. So think about it, class, even as the child swings, is the distance from the top beam to like the seat of the swing ever changing? No. So it stays the same. That's why it looks like it's staying the same in that graph. So then function S must be this one, which says the total number of times an adult pushes the swing as a function of time since the child gets on the swing. We're going to have more functions like this tomorrow. But yeah, it looks like they're pushing them 1, 2, 3, 4, 5, 6 times. And they're not pushing them for every single second, right? They're pushing them like intermittent. So the number of swings. What's going on? We're not done with this activity. Okay, well, the whole point is domain and range. All we did so far was match them. So now we need to identify domain and range for each one. All right, so we match them. Now we're going to identify domain and range. So starting with the first one that we matched, what are my possible inputs? What are we labeling the x-axis as? Time in seconds. And wouldn't that be true for all of these? So if you want to kind of do that for all of them, you can. And domain refers to all the what of a function. So what are my possible x's for this? Where does it start at, my x's? And where does it end at? When we reread the description, which is on your paper, 30 seconds. So you could summarize it. You could say all, is it just whole numbers? Could it be fractions of seconds? Could you have a decimal of a second? So if that's true, you can have decimals of seconds, then it can be 0.5 seconds, 0.6 seconds. So really all the numbers, not just whole numbers or integers, all numbers from 0 to 30. Now, here's how you would represent it more mathematically. Since this is like my lower boundary, and this is my upper boundary, for every boundary, you use an inequality, especially if it's all the numbers in between. So the way that I would represent that, I'd use X because we're talking about domain. And I'd show that all my X's on this line are from 0 to 30. That's how I represent it. Because all the X's are greater than 0, all the X's are less than 30, and they include both numbers. Does that make sense? So this should be the same domain for all of them. Just so you know, because that's not changing. What's changing is what we're putting on the Y. So for function H, what's going on the Y? The height in feet. Let's see, I don't think it mentions anything about the feet. Let's see. All right, it doesn't say like what the feet is from here, like it's not labeled. But what could it absolutely not be? Does it actually say? Because I have something written on my paper that seems like it says something. Okay, maybe we're missing some information. But on mine, I have that this starts at 1.5 feet. And that my height, my maximum height is 4 feet. So now with that additional piece of information, how would I write my range? What's my lower boundary? 1.5. What's my higher boundary? And could it be all the decimals in between 1.5 and 4? So then I'm going to use an inequality, and it's going to be really similar to how I did over here, except range is referring to all the what of a function. So back to your definition, range refers to all the, so I'm going to use the letter Y. And then if you always put your lower number here, your higher number there, it would always be this symbol. All these Y's on my line are bigger than 1.5, but smaller than 4, and it includes those numbers. Make sense? Okay, scrolling to the next one, make sure we're kind of being fast if you know. Can't stay on the same side forever. All right, so function R. We mentioned earlier the domain is going to be the same. That part's not changing. In each of these, what's changing is what's on the Y. So for function R, what should go on the Y? Does this one mention anything about height? So then not feet. So time left on the swing, and we're going to use seconds again for what's left on the swing, right? Versus when she was kind of past. All right, so what's my smallest Y value then? Zero. What's my biggest Y value? So here's where Y is 0. Where's my biggest Y value? 30. Because we know she was on the swing for 30 seconds. So the most she could have left is 30 seconds when she first got on the swing. And really what's going to be the only difference from the domain to the range? We're going to use the letter Y. But that's how you would represent it. Because we do have fractions of seconds. So really everything from 0 to 30 and in between is what my range is going to be. Questions on that? Okay, let's put power curve. Domain is going to be the same for all of them. I mentioned that before. That's not what's changing. What's changing is what goes on the Y. So for function D, what should go on the Y? The distance in feet. Now, is there any change? No. I don't know what the height is. Let me see if I have it in my notes somewhere. But yeah, so if I give you a little piece of information and tell you that this is at a height of 7 feet, what is my range going to be equal to? Could it be any number other than 7? So when it's just like a list of numbers, not like an interval, then this is how you represent it. Like that. Sometimes you'll see the fancy brackets around it. We'll practice that maybe another day. But we're saying my range equals 7. Can't be anything else other than the 7. all of my y's. So if it's just a list of numbers, then you would put commas. Like in that camper situation, it was like 200, comma 240, comma 280, and so on. All right, last one for the day. Questions at all? Okay, so function S, domain should still be the same. That's not changing in any of these situations. But for my range, what is going on the y-axis? What is this representing? Number of pushes, if you reread this. And what's my smallest y value? 1. Are you sure? 0. And then could it be fractions? Can't have a fraction of a push. What's her maximum number of pushes? Or 0, 1, 2, 3, 4, 5. And it's all the whole number. So since it's only these, you could list them like that. You could put it as an interval and specify only the whole numbers, like this. But something to that effect. All right, but you have to specify it's not decimal for that one. That's 2 ways you could represent that range. All right, sorry it was a little rushed. At least now I know for the rest of my classes to spend less time on the card sort. But that's all.